Welcome to Module 6, Configuring Network Addressing and Internet Connections. This module covers how devices actually get online, internet connection types, TCP/IP fundamentals, network communications, and network configuration concepts. By the end of this module, you'll be able to compare internet connection types, use basic TCP/IP concepts, compare protocols and ports, and compare network configuration concepts. These 4 outcomes map to the 4 lessons ahead. Lesson 6.1, Internet Connection Types. This lesson maps to 2A plus 2.201. 2.01 Objectives. 2.5, Comparing common networking hardware devices, and 2.7, Comparing internet connection types, network types, and their characteristics. By the end of this lesson, you should be able to answer: what internet connection types does an ISP provide? What networking hardware connects you to an ISP? What are IPv4 and IPv6, and how do they let networks communicate? What are TCP and UDP, and how do they differ? What ports and protocols show up on SOHO and ISP networks, and how do DNS and DHCP help configure a network? ISPs offer several connection types. Cable internet uses coaxial cable, fast and widely available. DSL uses telephone lines, with speed depending on distance from the ISP. Fiber offers very high speed and low latency, though rollout is still limited. Satellite provides global coverage but higher latency. Cellular, over 4G or 5G, gives you wireless internet through mobile networks. And dial-up is a legacy option, very slow and now rare. Connecting to an ISP takes a few hardware pieces. The modem converts the ISP's signal cable, DSL, or fiber into digital data. The router directs traffic between your local devices and the ISP. A switch connects multiple local devices inside the LAN. An access point provides wireless connectivity. And a firewall, sometimes built into the router, protects against unauthorized access. TCP, or Transmission Control Protocol, is connection-oriented and reliable, using error checking and acknowledgements. You'll see it behind HTTP, HTTPS, FTP, and email. UDP, or User Datagram Protocol, is connectionless and best effort, faster with less overhead, used for DNS lookups, VoIP, streaming, and online gaming. DNS, the domain name system, translates human-friendly names like google.com into IP addresses. DHCP, Dynamic Host Configuration Protocol, automatically assigns IP addresses, subnet mask, gateway, and DNS server, cutting down on manual configuration errors. Here's what this lesson covers: DSL modems, cable modems, fiber to the curb and fiber to the premises, fixed wireless internet access, and cellular radio internet connections. An internet connection typically involves Internet Exchange Points, or IXPs, and Internet Service Providers, or ISPs. The modem converts the ISP's signal, cable, DSL, or fiber into digital data your router or PC can use. Think of an IXP like a train station. Instead of every train going directly to every destination, they meet at the station so data can switch networks and reach its destination faster. Continuing on modems, the router is what identifies networks and forwards data between them, acting as the traffic manager between your local network and everything beyond it. DSL runs over the public switched telephone network, the plain old telephone system. Asymmetrical DSL gives you fast downloads but a slower uplink, which is fine for most home use. Symmetric DSL offers matching upload and download speeds, making it the better choice for businesses that need to send a lot of data upstream. Cable modem installation follows a specific chain. The modem interfaces with the ISP's network over coax, terminated with F-type connectors, then connects to the local router via an RJ45 port. The router connects to a local switch, and local devices connect to that switch. These days, many providers ship an all-in-one device combining the modem, router, switch, and wireless access point. Copper cabling runs into limits on speed and interference, which is where fiber solutions come in. Fiber to the curb, or FTTC, runs fiber close to your home, to a nearby pole or box, then finishes the connection with copper. Fiber to the premises, or FTTP, runs fiber all the way to your home or business for the fastest, most reliable speeds. Here's what fiber to the curb and fiber to the premises actually look like installed. Notice where the fiber to copper transition happens in each case. Fixed wireless internet access, also known as satellite internet, think HughesNet or Starlink, fills gaps in rural areas and older buildings where running new cable isn't practical. The options include geostationary satellite internet, low Earth orbit satellite internet, and wireless internet service providers, or WISPs. Cellular internet has evolved through generations. 3G relied on GSM or CDMA-based handsets. 4G introduced LTE devices. 5G is a more complex rollout, requiring many small antennas and massive MIMO, multiple input, multiple output technology. A router forwards data packets through the internet using IP addresses. A LAN router divides a single physical network into multiple logical subnetworks, while a WAN router forwards traffic to and from the internet over a private WAN link. Think of a router as a traffic manager, deciding the best path for data, whether moving traffic within a large enterprise network or sending it out to the internet. Here's what a router looks like in practice. Notice the ports for WAN, LAN, and often built-in Wi-Fi all in one device. Firewalls filter allowed and denied hosts and protocols using an access control list, or ACL. On a private network, they can limit client connections to specific servers, and can run as a standalone appliance for deeper protocol analysis. Think of a firewall as a security guard for your data. A client-based firewall like Windows Firewall runs on the device itself, while a hardware firewall is a standalone appliance filtering traffic for a whole network. Lesson 6.2. TCP IP Concepts. This lesson maps to A+2-201-201, Objective 2.6, Configuring Basic Wired and Wireless SOHO Networks. By the end of this lesson, you should be able to answer: what are the layers of the TCP IP model? What are the differences between IPv4 and IPv6? What are the IPv4 address classes? And how does DHCP allocate IP addresses? And what happens if it fails? The TCP IP model has 4 layers. The application layer handles user services like HTTP, FTP, DNS, and SMTP. The transport layer manages end-to-end communication through TCP and UDP. The internet layer handles logical addressing and routing through IP and ICMP. And the network access layer covers the physical and data link level, Ethernet, Wi-Fi, cables, and NICs. This is often shown as 4 layers, compared to OSI's 7. IPv4 uses 32-bit addresses, about 4.3 billion total, written in dotted decimal, like 192.168.1.10, with a limited address space that requires NAT to stretch further. IPv6 uses 128-bit addresses, trillions available, written in hexadecimal and colons, like 2001 DB81, with built-in security through IPsec, auto-configuration, and no need for NAT. IPv4 addresses break into 5 classes. Class A spans 1.0.0.0 to 126.0.0.0 with the default /8 mask, used for large networks. Class B spans 128.0.0.0 to 191.255.0.0 with a /16 mask for medium networks. Class C spans 192.0.0.0 to 223.255.255.0 with a /24 mask for small networks. Class D, 224.0.0.0 to 239.255.255.255 is reserved for multicast. And Class E, 240.0.0.0.0 to 255.255.255.255 is experimental. DHCP allocates addresses through a 4-step process known as DORA: discover, where the client broadcasts a request; offer, where the DHCP server replies with an IP lease; request, where the client asks to use that offered IP; and acknowledge, where the server confirms and assigns it. If DHCP fails, Windows falls back to APIPA, automatic private IP addressing, assigning an address in the 169.254.x.x range, but that device can only talk to others on the same APIPA subnet with no internet access. Here's what this lesson covers: TCP IP's link or network interface layer, internet layer, transport layer, and application layer, along with IPv4 addressing, network prefixes, and IPv4 forwarding. Continuing the roadmap: public and private addressing, IPv4 host address configuration, static versus dynamic configuration, SOHO router configuration, and IPv6 addressing round out this lesson. TCP IP, the Transmission Control Protocol/Internet Protocol Suite, is the set of rules that lets network hosts communicate data in a structured format. It's organized into 4 layers of function: application, transport, internet, and link or network interface. Here's the 4-layer TCP IP model laid out visually. Each layer handles a distinct part of getting data from one device to another across a network. The link, or network interface, layer puts frames onto the physical network using local media like Wi-Fi, DSL, or a cable modem. Communication at this layer happens only on the local network. It doesn't cross network boundaries. The internet layer handles packet addressing and routing across a network of networks. Messages from IP at this layer get delivered by ARP, the Address Resolution Protocol, to host interfaces addressed at the link layer below. The transport layer is implemented by one of 2 protocols. TCP, Transmission Control Protocol, is reliable and used by most applications. UDP, User Datagram Protocol, is unreliable but faster with less transmission overhead. TCP checks for errors and confirms receipt. UDP just sends the data without those guarantees. The application layer performs high-level functions with numerous protocols in the TCP/IP suite configuring and managing network hosts to run services like web and email. High-level protocols handle specific tasks, requesting a web page, sending an email, moving a file, while lower-level protocols like TCP support them underneath. Putting the four TCP/IP layers together, the application layer interfaces with user applications through protocols like HTTP, FTP, SMTP, and DNS. The transport layer manages end-to-end communication and segmentation through TCP and UDP. The internet layer handles logical addressing, routing, and best effort delivery through IP, ICMP, and ARP. And the network access layer governs physical transmission across local networks through Ethernet, Wi-Fi, and PPP. IPv4 addressing assigns 32-bit numbers to devices, arranged in 4 groups of 8 bits, something like 11, 00001, 01, 01, 01, 01, 01, 001, 0000, 0000, in binary. Dotted decimal notation exists to reduce human error when entering these addresses. Here's an example of that dotted decimal notation, showing how the binary groups translate into the familiar 4-number format you'll actually type and read. Here's network prefixes shown visually. Notice how the subnet mask lines up against the IP address to separate the network portion from the host portion. When a host sends a packet over IPv4, it compares the source and destination against its own subnet mask. If they match, the destination is assumed to be on the same IP network. If they don't match, the host assumes the packet needs to be routed to a different IP network entirely. Here's IPv4 forwarding shown visually. This is the comparison a host runs every time it sends a packet, deciding whether to deliver locally or route it elsewhere. 2 more forwarding examples. One showing matching source and destination network IDs, staying local, and one showing different IDs, which means the packet has to be routed to another network. Time for an activity. Troubleshooting network issues. Identify the problem using tools like ping, ipconfig, and tracert. Resolve it by reconfiguring network settings, and document the steps you took to fix it. Public IP addresses are assigned by your ISP and routable on the internet. Private IP addresses aren't routable on the internet at all. Class A covers 10.0.0.0 to 10.25, 5.255.255. Class B covers 172.16.0.0 to 172.3, 1.255.255. And Class C covers 192.168.0.0 to 192.168.255.255. Private addresses reach the internet through NAT, Network Address Translation, where the router translates private addresses to public ones, keeping the internal network hidden in the process. A host needs 4 pieces of configuration to communicate: an IP address, a unique number like 192.168.1.25, a subnet mask defining the network portion like 255.255.255.0, a default gateway, the router's IP and the path to other networks, and DNS servers, which translate domain names into IP addresses. Without all 4, a host can't communicate outside its own subnet. Static addressing means manually entering the IP, subnet mask, gateway, and DNS, used for servers, printers, and anything that shouldn't change. Dynamic addressing, through DHCP, has the server automatically assign all of that, common for desktops, laptops, and mobile devices. And APIPA, automatic private IP addressing, is the backup when a DHCP server is unreachable, assigning an address in the 169.254.x.x range that only allows local subnet communication with no internet access. A SOHO router has 3 key interfaces: a WAN port connecting to the ISP modem on the public side, LAN ports for local Ethernet devices, and a Wi-Fi access point for wireless clients. Basic setup. Connect to computer via Ethernet or Wi-Fi. Configure it for automatic IP through DHCP. Open a browser and enter the router's default IP, often 192.168.1.1, log in with the default admin credentials, and immediately change that default password for security. Time for a lab. Network configuration. Access the router's management interface. Configure a DHCP scope for automatic IP assignment. Set up a static IP for a printer. Configure DNS settings, and test the network by pinging devices and accessing a website. IPv6 addresses are written in hexadecimal, separated by colons, something like 20010DB885A3 8A2E037073334, with runs of zeros shortened using a double colon. The 128-bit address splits into 2 halves. The first 64 bits are the network ID, like a street name, and the last 64 bits are the interface ID, like a house number. A global unicast address is public and routable on the internet, while a link local address is auto-configured and only works within the local network. Many devices run dual-stack IPv4 and IPv6 together, until full IPv6 adoption happens. Welcome to Lesson 6.3 on Network Communications. This video aligns with A+ Exam Objective 2.1, where we compare and contrast TCP and UDP protocols, their ports, and their specific purposes. By the end of this video, you'll be able to define TCP and UDP, explain how they differ as communication protocols, identify the standard protocols, and know the default port numbers for each. First, what are TCP and UDP? TCP, or Transmission Control Protocol, is connection-oriented and ensures reliable delivery. UDP, or User Datagram Protocol, is connectionless, fast, and lightweight, prioritizing speed over perfect delivery. To understand the difference, consider this analogy. TCP is like certified mail with tracking and confirmation, while UDP is like a postcard, sent quickly but without a guarantee that it will arrive. This table provides your at-a-glance reference for standard communications protocols, their default ports, and whether they typically use TCP or UDP for transport. Throughout this lesson, we will cover the core aspects of network communications, including protocols, ports, the specific functions of TCP and UDP, and common well-known ports. Ports act as virtual doorways, allowing multiple applications to share a single network connection. Each application uses a specific port number to identify its communication, managed at the transport layer. TCP is a connection-oriented protocol. It ensures reliability by establishing a connection, using sequence numbers for ordering, retransmitting lost packets, and performing a graceful termination of the session. UDP is connectionless and faster, making it ideal for time-sensitive data like streaming or VoIP. Common examples include DHCP for IP assignment and TFTP for simple file transfers. Key well-known ports to remember include 20 and 21 for FTP, 22 for secure SSH connections, 23 for Telnet, 25 for email via SMTP, 53 for DNS, and 67 and 68 for DHCP. Other essential ports include 80 for HTTP, 110 for population, 143 for IMAP, 389 for directory services, 443 for secure web browsing, 445 for SMB, and 3,389 for remote desktop access. Now, let's move to Lesson 6.4, Network Configuration Concepts. This lesson covers A+ objectives regarding services provided by networked hosts and common network configuration concepts. In this next section, we will learn about the purpose and capabilities of the Dynamic Host Configuration Protocol, the purpose of the domain name system, and the role of VLANs. The primary purpose of DHCP is to automatically assign IP address settings to devices. This simplifies management and eliminates the common errors associated with manual configuration. Beyond just assigning IP addresses, DHCP provides subnet masks, default gateways, and DNS server info. It also supports lease times for temporary assignments and reservations for specific devices. Let's look at the Domain Name System, or DNS. Its purpose is to translate human-readable names like Google.com into IP addresses. It's essentially the Internet's phone book, making it easy for users to access websites without memorizing complex numbers. VLANs, or Virtual Local Area Networks, allow you to logically segment a network into smaller groups without needing separate physical switches. This separation improves security and performance by isolating traffic and reducing broadcast domains. This module explores core configuration concepts, DHCP, DNS, DNS queries, various DNS record types, VLANs, and VPNs. Understanding these is fundamental for managing modern network environments effectively. Let's dive deeper into DHCP functions. A DHCP scope defines the pool of IP addresses available for distribution. Devices then lease an address for a set duration, or you can create a reservation to ensure a device always gets the same IP based on its MAC address. Regarding DNS, it uses fully qualified domain names, or FQDNs. An FQDN combines a host name with a domain name and suffix to ensure global uniqueness. These are managed by a hierarchy of servers, including the 13 root-level DNS servers. Here is a high-level view of the DNS hierarchy. It flows from the root servers down to top-level domains, then to authoritative name servers that hold the final records for specific domains. When a query is made, your device checks its local cache first. If it's not found, it queries a configured DNS server, which then traverses the hierarchy from root to the authoritative server to find the correct IP address. This diagram illustrates the step-by-step process of a DNS query, showing how a request travels from a client to the authoritative server and back to the requester. DNS records serve various functions. A records map names to IPv4 addresses, while A handles IPv6. CNAME acts as an alias. MX identifies mail servers. PTR handles reverse lookups, and SRV defines network services. Spam management is critical. TXT records store data for SPF, DKIM, and DMARC. SPF lists authorized senders. DKIM signs email to ensure integrity. And DMARC provides instructions on how to handle mail that fails these checks. VLANs provide logical segmentation. By grouping devices into distinct VLANs, like keeping employees, guests, and servers on separate segments, administrators can greatly enhance network security and manage broadcast traffic more efficiently. VPNs, or virtual private networks, create a secure, encrypted tunnel through the public internet. This allows remote users to connect to their private office network securely, as if they were physically connected at the office location. To summarize, IT professionals use these protocols to ensure network hardware is functional. The TCP/IP suite is the standard for configuring these devices, enabling reliable local and internet-wide communication. Finally, remember that each protocol has specific parameters for communication. Mastering these configuration concepts is essential for understanding how servers provide services to the nodes across the entire network infrastructure.